Okay, this is our last tank problem. The tank looks like it is in the picture, and it says that the trough has triangular cross sections and that it's 3 meters tall and 3 meters across. So what we know there, 3 meters high, 3 meters across, is that it's as tall as it is wide, or wide as it is tall. Each of those orange distances is a distance of 3. Then the length of the base is 8, and the spout is at a height of 2. So if we make this 0, and then this is 3, the spout is at a height 5 because it's 2 above the top of the tank. And we're going to do two things: an integral to pump it all the water out if it's full of water, and then if it's half full, pump all of that. So here, let's draw in a slice of water. The water pumps out vertically. So here's a slice of water, and let's see, color that in. There you go. And that water slice is currently at some height y. So let's find the area of a slice, the distance a slice moves, and then we'll talk about our bounds. So the distance a slice moves is the spout height minus its current height. That's 5 minus y. The area is the area of this rectangular slice. The distance down the side is 8, and the distance across is y, because whatever height the slice is at, it's also that far across. That's what 3 and 3 is telling us. If that slice is at height y, then it's also has width y. The triangle's a distance of y across. So the area of a cross section is 8y. Let's talk about the tank being full of water, pump all that. Full of water, pump all water. The bounds would be 0 to 3. That's the bottom of the tank to the top. If the tank was half full, and pump all of that. Pump all water. The half full would be 0 to 3.5. Bounds would be 0 to 3.5. Then let's write our integrals. The work in the top case, let's move this one down here. Here, the work. We're dealing with water again, so this in bounds are 0 to 3. 1,000 for the density of water, 9.8 times gravity. Distance it moves is 5 minus y. Area of a slice, 8y dy. That's the work. In the first case, to pump all the water out of the tank when the tank was full to begin with. In the other case, let's see, did I say 0 to 3.5? I said 3.5, but it's 3.5, so it should be 1.5 for the bounds. 1.5, the work here, 0 to 1.5 is the tank being half full in terms of height. We're pumping all of that section, and that's 1.5. So then the rest of the integral doesn't change. 5 minus y, the area is still ay dy. And then the question in the problem is whether or not pumping half the water takes half the work. And you'll see that it doesn't here. Let's see. Okay, so this integral here, this is a 3. This is a 3, and we're cutting it in half, and then 0 to 1.5. So this integral is our tank full pump all the water. This integral is that same integral, but scaled by half. Scaled by half. And then here's our half full pump all water. So here's the full amount of work to pump a full tank empty. This is half of that. And then to pump a half full tank, all of that work, we have the 352,800 joules. So no, it doesn't require half the work to pump a half full tank empty. All right, if you have any questions, please reach out and I'll see y'all soon.